As David said earlier, I'm a data scientist at Deliveroo, and at Deliveroo I work largely on questions of causal inference, with a focus on experimentation methodology, and that's basically where today's talk stems from. It was a project that I worked on recently at Deliveroo, where we tried to elevate the methodology we use in analyzing cluster randomized experiments, and I'll hopefully talk about that, or like at the end of the talk, you should have a much better idea about what I mean by that. So in today's talk, I want to use the analysis of a hypothetical experiment where I just simulated some data to discuss 3 points, really. The first one I want to touch on is the statistical model most often used for experiments. And I want to talk about that because that influences really the properties of the estimators that we commonly use in analyzing experiments. And then I want to, in points 2 and 3, use that background to basically discuss, in the context of that hypothetical experiment, the analysis of one metric where the unit of randomization is the same as the unit of analysis. And that's basically standard fare for most people. And then I want to also discuss the analysis of a metric where the unit of randomization is coarser than the unit of analysis. And that is really what I mean by a clustered randomized experiment. In the context that we'll be talking about it, it will be an experiment randomized at the user level, but we want to analyze an outcome metric at the order level, so an order placed with Deliveroo. So to be a bit more precise about this whole thing, let's imagine that we want to test a new marketing campaign that involves sending personalized emails to users. So we'll split our sample of users into a group of control recipients that do not receive any emails or receive the standard emails that we send, and a group of treatment users that will receive some personalized email that contains different content or is differently formatted or whatever you can think about. For simplicity's sake, we assume an even split between treatment and control, but that is by no means necessary for what we'll talk about later. As I say on the slide, we choose to randomize at the user level. And 2 metrics that we want to follow in this experiment are a total user orders per user level. So the question of how many orders did the users in the experiment place in the treatment compared to the ones in the control group. And we also want to understand whether the users changed their order value behavior. For example, ordering more items, ordering for a larger group, and thus hopefully the marketing email would allow people to order or encourage people to order at a higher order value. Now, what I said earlier is basically about the difference between the randomization unit and the analysis unit. Hopefully becomes clear here. Total orders per user is a user level metric, whereas order value is an order level metric. And that's where the randomization unit is now coarser than the analysis unit. But before we actually talk about the analysis of the experiment, I want to briefly talk about what has been dubbed the Rubin causal model, which is the statistical model that underlies most of the literature that talks about evaluating experimental methods or methods for experiments. And it's actually really elegant, somewhat intuitive when you think about it, but it's only intuitive after the fact. Rubin, when he formalized the whole thing, I don't think it was quite as well understood that that's the way to think about experiments. And the model, or like the whole idea, the context of talking about it is probably easiest explained with a very small example. Imagine that we have 4 users here, users 1 through 4. And these users have potential outcome metrics both under control 0 and treatment 1. So if they receive the email that is the current standard, the control group, they will have a specific outcome, say for the number of orders they place. And if they receive the treatment 1, all of them also have a different an outcome under that world. The causal effect then is simply the difference between the two. What would have happened under treatment minus what would have happened under control. And if you make this a bit more precise, you can see that here in this hypothetical example that I assume user 1 would place 1 order if receiving the current status quo email, but would double that to 2 orders if they receive the email that we want to test in the experiment. the causal effect then would basically be 1 for this user. Note, however, that it doesn't have to be positive. User 2, for example, places 3 orders right now, and for some reason doesn't quite engage with the email under treatment as much, reduces that to 1, so the causal effect there is -2. So the causal effect here is already assumed to be heterogeneous across agents, and what people in experiments most often estimate is the average treatment effect. So basically the average over all those causal effects. In this experiment, it would be 0.25. So rolling out this campaign would increase orders per user, total orders per users by 0.25. That may or may not be a lot. The way it's obviously like the way to calculate the average is a little, it's obvious how to do it. The only reason why I want to briefly mention this is because the idea of calculating first all the totals for users in treatment minus all the totals for the users in control, or for the outcomes in control, and then dividing by 4 is a way of calculating the mean that will become a little more important further down the line. So the randomness in these experiments is assumed to come from the assignments into treatment or control. So note that we can't have all users both in treatment and in control during the experiment. So we need to randomize. Some will see the email in treatment and some will receive the standard. And it's that difference in assignment that creates the uncertainty that people talk about when they think, for example, about statistically significant effects. So for one example, imagine that users 1 and 2 receive treatment, but users 3 and 4 do not. Then the observed outcomes would be 2 and 1 for users 1 and 2, and 5 and 2 for users 3 and 4. So the average treatment effect that we would estimate here is the total of all the outcomes in treatment per user divided by 2, scaled to all users 4 in the population, minus the appropriately scaled outcome in control, divided by 4 to come back to the user level, and then the estimate would actually be -2. Note that the true estimate is 0.25, but the true value is 0.25, but the estimate we came up with in this assignment is -2. If we had chosen a different assignment where users 1 and 4 would have been in control, but 2 and 3 in treatment, the estimate calculated the same way would have been 3. So you can already see that depending on which assignment actually happens to be realized in your specific experiment, your estimate may or may not be close to what the true value is, and in fact may have the wrong sign. And that's where the statistical inference for this whole endeavor comes in. Contrast this with sampling uncertainty, which is what's commonly assumed in most textbooks when they discuss statistical methods, and in particular least squares estimation, OLS. Sampling uncertainty stems from the idea that you're drawing a fairly small sample from a much, much larger population. And the uncertainty then is about having drawn that specific subset of units with their outcomes as opposed to some other subset with different outcomes. And had you drawn different units, you would have seen different outcomes. The results discussed in many standard textbooks based on sampling uncertainty do not easily transfer to experiments. So it's not always clear that what you think you know about OLS in a general model with sampling uncertainty is actually true for an experiment where the source of uncertainty is assignment uncertainty. And I'll talk about a couple of those later. One of the most surprising ones to me when I first learned about this is the fact that OLS estimates aren't actually unbiased in an experiment. And that has implications for using covariates, as I'll show you in a second. Which one actually matters, assignment uncertainty or sampling uncertainty? It's not clear that there is a clear-cut choice that makes one right and the other wrong. I think it depends a bit on the context of the experiment that you want to run. If, for example, you experiment on a very large fraction of your user base, then assignment uncertainty is probably the more relevant and more prevalent form of uncertainty rather than sampling uncertainty, only because you already choose an extremely large fraction of your user base And had you sampled differently, the outcome probably would not have been very different. In the extreme case where you experiment on the entire user base, there's basically no sampling uncertainty left. Just for those people who wonder whether you can't have your cake and eat it too, there are some early attempts in the literature that try to combine both aspects into a single model, and that is possible, although leads to some fairly complicated notations. I have a reference here at the bottom for people that are interested in looking into this. It's a pretty interesting aspect of the literature. Okay, so with that idea of uncertainty and the source of uncertainty out of the way, let me now go back to the actual experiment that we're thinking about analyzing. In the following, I want to highlight some of the implications that stem from this framework for the analysis of an experiment. And in this first bit where we try to analyze total orders per user, we're going to focus on the case where the randomization unit is identical to the analysis unit. Both of those are done at the user level. And in that case, most people would probably start off with a very simple difference in means estimator. So the treatment effect, the average treatment effect estimator, which I call tau here, for the difference in mean estimators is really simply just the difference between all observed outcomes in treatment minus all observed outcomes in control. And the way you would formalize this a little bit is exactly as we had done before, right? So the inner sum here of all observed outcomes, y over the set of all users in treatment, is divided by the number of users in treatment, nt. That gives you the number of orders per user in treatment. You multiply by the number of all users to scale it up to the average, to the number of users, number of orders for all users had they received treatment. That's the scaled estimate. You did subtract the number of orders for those people in control. You divide by the number of all users, and that gives you the average number of orders per user. So the difference between treatment and control. Had you done this at the population level as opposed to your sample level. This is just a way of writing the difference in means, and I hope that that helps with later discussing some of the bias issues that can arise. The variance estimator, that is also a standard formula that probably, hopefully looks familiar to many of you. It's simply the variance of outcomes in treatment divided by the number of users in treatment plus the variance of outcomes in control divided by the number of users in control. And then the standard deviation would be the square root of that. Now, many people would start with the difference in means estimator when they analyze the experiment, but they wouldn't stop there, rightly so, because they would say, look, I have some very good pre-experiment covariates that help me, or should help me in theory anyways, improve my inference on the treatment effect. And the way many would do this is by running a little regression of the outcome y on an indicator w that states whether the observation was in treatment or control, and add in some controls. Most of the time, people would demean those controls only because there's a constant already in there and you want to make sure that you properly interpret them. The coefficient on the constant. But it doesn't matter hugely whether or not you demean them. The simple difference in mean is very good, but with controls, you would reasonably expect that you have more accurate inference. Now, the interesting bit, if you model, if you thought about this regression in terms of sampling uncertainty, you would say, well, naturally, if the model is correct, if it's actually linear, and if my coefficients are constant, and if certain requirements on the residuals are satisfied, then this is an unbiased estimator. And in fact, under slightly stronger assumptions, it's the best linear unbiased estimator. But it certainly is unbiased and almost even with weaker assumptions. That is no longer true in the model, in the Rubin causal model, where the uncertainty stems from assignment uncertainty. So the first sort of message here is that if you use covariates, please do use them with caution because your estimator is no longer unbiased. The unbiasedness comes essentially from the fact that the model does not assume that the actual relationship is linear, nor does it assume that the treatment effect is constant for across individuals. As I had shown in that earlier table, it's very well possible that the treatment affects different users differently. And if you drop these two assumptions, then that estimator is no longer unbiased. The good news is, however, that the estimator shrinks in the number of users or the number of observational units. So in most experiments that are moderately or large, let's say thousands of people, I would expect the estimator to have very little actual bias. What may be worse, though, is that if you do use covariates, please always interact them with the treatment indicator as indicated in that third summand here. If you don't do that, the precision from the regression-based estimator might actually be worse than the simple difference in means estimator. And that has to do with the fact that you assume that the effect of the pre-treatment variable on the outcome y is the same for treatment and control if you don't interact. And if that assumption isn't given, then you might actually end up with a precision that is worse. So the safe thing to do is always to interact them. And the last thing I would say on the problem of the bias is if you run both the difference in means estimator and the regression-based estimator, I would expect them to be very close in outcome if the bias doesn't play a big role. If they're wildly different, you might have to analyze the data a bit more closely to make sure that nothing undue is going on. If you run the analysis, if you estimate the treatment effect through a regression like that, then the easiest way of deriving this variance formula is by simply using what's called HC0 standard errors. And you can do that in Python by specifying the cov type, the covariance type. In R, there are many different options. One I am aware of is this package vcovcl, but I think there are a couple of others as well. And those give you the standard variance formula that you should be using. And in particular, it allows for the assumption of the variance being different in treatment and control. As I said, if you want to, or if you analyze it at the same level as the randomization unit, then and you want to use covariates, always interact them with your treatment indicator and run both the simple difference in means and the regression estimator to compare the outcomes and make sure that bias isn't actually an issue in your particular application. Now I want to move to the experiment where the randomization unit is actually coarser than the analysis unit, and that was the case of our order value outcome, where we're now trying to understand the average outcome for treatment orders relative to the average outcome for control orders. Now, in this case, even the simple standard estimator is problematic in that it is biased. So the difference in means estimator, again, is the difference in treated outcomes minus the average, difference in control in the average controlled outcomes. And again, as I did that on the previous few slides, one way of writing it is summing which looks like this somewhat unwieldy expression. If you focus on this yij ops here, this is the order value of user I for their order j. We sum all those order values for user I over all their orders, which now the orders for user I depend on, the number of orders of a user are specific to that user. Some users place 2 orders in the experiment, others might place 5 orders. So that sum goes through an index that is user specific. You sum it across all users in treatment, divide by the number of all orders, and that gives you the average order value in treatment, minus the average order value in control, and then that's the simple difference in means estimator. Trying to replace the total outcome for user I with the yi ops, now not depending on the observation j anymore, pretty much looks then very familiar to what I had done earlier in this very simple assignment table, where we just summed the totals for the treated units and divided by the number of treated orders. Now, if you wanted to understand whether or not that estimator is unbiased, then you would have to take the expected value of these expressions. Now the challenge comes in that the denominator is now a random variable. Remember earlier we were dividing simply by the number of users, and that is, once you do a specific split in an experiment, a fixed number, right? Like in our case, it was a 50-50 split. It would always be the same number of users in treatment and in control. The only thing that would vary is who are the ones in treatment and who are the ones in control. But the sum of the number of people in control wouldn't change. This is a user experiment, so it continues to be true that the number of users in treatment is fixed. It's always, say, if we experiment on 1,000 people with a 50-50 split, it's always around 500. But the total sum of the orders placed by these 500 people varies. It could be that the 500 people in treatment placed a lot of orders, more than average, and then that would be, the denominator here would be higher than in a case where the 500 people placed on average many fewer orders. So the total number of orders in treatment now becomes a random variable, and that causes the bias. The bias has to do with there being potentially correlation between the cluster totals yi ops and the number of orders placed, what I call the cluster size here. Strictly speaking, the bias is a function of the difference between that correlation in treatment and in control. But if there is a correlation like that, you'll likely face some bias, and the only question is how big is it? The second problem in a cluster randomized experiment is that the standard variance formula that we had derived on earlier slides is no longer valid. The derivation of that formula basically requires that the observations are independent. And in our case, the orders aren't independent anymore, right? Because the same number of orders placed by this, or a series of orders placed by the same person probably do not have an independently distributed order value. I might always order for myself and always from the same place, so the order values are probably pretty correlated, whereas others might always say order for their family. It's always family night out with a couple of children, and then those order values across orders would also be correlated. So in that case, the standard derivation isn't valid anymore. And in many cases, the variance estimated under the assumption of independence is smaller than if you allow for that correlation that I had just discussed. And because of underestimating the true variance, your inference becomes overly optimistic, in the sense that because of a variance that is too small, you end up deriving a t-statistic that is much larger than it should have been. And thus, if you then compare this to the standard normal, you would reject more often than you should, more often than the 5% that we usually think of as the type 1 error. For those of you familiar with it, we could use cluster robust standard errors, but I'll show you in a second that even those can lead to problems. And they lead to problems in cases where some clusters have really high numbers of orders. So for example, if there are some users in the experiment that are crazy power users and order way more often than everybody else, then these cluster robust standard errors don't always fix the problem. What does that look like in a specific example? What you see in the middle here is the standard normal distribution, and the gray area is the inner 95% area. So there's the bottom here is minus 1.96 to plus 1.96, outside of which a t-statistic we would reject under the null and say the result is significant. So what I did is I simulated an experiment, and then I calculated for that specific experiment the t-statistic for that specific assignment. I then permuted the assignments thousands of times, and for each one of them I calculated the t-statistic, and what I ended up with was this bimodal dash dotted line of the t-statistic. So two features that are already kind of obvious. The t-statistic derived that way with the standard variance formula used for independent observations has much, much more probability mass outside of the gray thresholds here than it should. If our inference was correct, that should only be 5%, but in this case, it's much, much more. So we'd be much more often making inference saying the outcome was statistically significant, even though it wasn't, actually. The other thing that I'll be touching on is the fact that it has basically two modes instead of just a single mode. And that sort of is a bit of an elephant in the room effect that I'll show you in a second. Now, I mentioned that cluster robust standard errors can sometimes correct this. And when I did the same analysis using cluster robust standard errors instead of the simple HC0 ones, you do see that now the green density estimate gets much closer to the standard normal density estimate. Now the area outside of the gray boundaries is much closer to 5%, even though it's still somewhat off. You could argue that it's actually much, much better and maybe even sufficiently good for your case. We still haven't gotten rid of this funny hump here, the bimodal hump. And I'll talk to you about that on the next slide. So where does that hump come from? And I said earlier that the results can be incorrect for the clustered standard errors if there is very large skew in the cluster sizes. And the experiment that that are randomized, you have many users there in the bottom left-hand corner with order values. As I said, this is hypothetical, somewhere around what is like 0.5 and in the range of like 1 to say 15 orders. And then there's Adam. Adam places over 60 orders and has an order value that is more than 7 times larger than some of the other biggest orders. So he's sort of an elephant in the room. He's a really, really large cluster. And that's basically what causes the issue. What happens is that the bimodal effect shows up when Adam, so one of the modes is those experiments where the assignment is such that Adam ends up in control. And the other mode happens when Adam shows up in treatment. This like skew in the cluster sizes can lead to this bimodal effect in the distribution, and getting rid of that is what I'll basically talk about in the following. So before we get to removing this bimodal effect and the issue with cluster skew, let me first talk about removing the bias in the estimator. So if we rewrite the estimator in this sort of scaled fashion that we discussed earlier, then you see that this is the total number of, or the total value of all orders in treatment divided by the number of orders in treatment, scaled by the number of orders overall to come up with the overall order value under the outcome of treatment. And then we divide it by N0 to come up with the average. And the same holds for control over here. As I said earlier, the issue has to do with the fact that the total number of orders in treatment is now a random variable, because depending on which user gets assigned to treatment and which one gets assigned to control, the total number of orders varies. I had also mentioned that a number that is fixed is basically the number of users in the experiment, in treatment and in control, right? So the alternative estimator takes the order value total and scales it not to all the orders, but to all the users to come up with a population estimate of the order total. So just as before, it sums all the order values in treatment, but now instead of dividing making that a per order estimate, it makes it a per user in treatment estimate. And then scales it up not to the number of all orders, but to the number of all users in the population. And after that, it divides by the number of orders to come up with an order level estimate of the treatment effect. Just like with the analysis of the user level metric, And just like there, that metric was unbiased because the number of users in treatment and control was stable across assignments. Now this number here, the red one, is also stable across assignments, so that the whole estimator is unbiased. We still haven't fixed the scaling, the variance instability issue with the sort of elephant in the room. Like Adam still poses a challenge even for this estimator. The way to try to fix that introduces a correction factor to the way that we calculate the order value total. And that's basically the red term that I've introduced here. Ignore k for a moment and think of k just as a scaling constant. I'll talk in a second how we actually calculate this. But then the way that this, which is also called a Desrage estimator, that's why it's called DR here. The way this estimator works is that it calculates the total order value for user I, but then it scales that depending on whether that user placed more orders ni0 than the average n0 over n, or fewer. So the parentheses in red here are basically the deviation of the number of users or orders placed by the user relative to the average number of orders placed by a user in the experiment. If the adjustment factor k is positive and you place more orders than the average, we would scale your total downwards. If you place fewer orders than the average, we scale your total upwards. Well, basically, and that way we shrink basically the very large range you had seen from these people in the lower left-hand corner to Adam in the upper right-hand corner. We shrink that on the y-axis to be much more aligned with sort of across users. It's not immediately obvious why this is an unbiased estimator, but if you were to try to calculate this, it turns out to be an unbiased estimator. And the idea has to do with the fact that on average, the number of average orders is basically, like on average, this term here is 0. So then when you take the expected value, this adjustment term disappears and you recover the true average treatment effect again. Now, for that to be true, k needs to be somehow determined without any data within the experiment. Because if they were used within the experiment, then that isn't, then strictly speaking, the bias, it would not be 0. And that already touches on what k really is. K is meant to be a prior estimate of the correlation between cluster totals and cluster size. And that pretty much reflects in our experiment, the setup, right? Where we saw a slightly positive correlation between the cluster size or the number of orders and the total order value per user. In this case, k was positive, and as you will see on the next slide, it was actually downward adjusted. The original estimator stems from the sampling and survey literature, and there it's actually fairly challenging to come up with plausible estimates of k, because you need data that are unrelated to the experiment. For many modern data science applications, especially in tech companies, it's actually not that difficult to come up with plausible estimates for k, because we almost always have pre-experiment data that relate the same or sort of record the same outcomes, total number of orders for users, total order values for users, and we can use k from previous periods to try to apply it to our experiment. So what does the application look like? Remember, the blue ones were total values per order before the adjustment, and Adam was this very large outlier in the upper right-hand corner. With the adjustment, because k, as I said, was positive, and Adam places many, many more orders than the average user, the adjustment brings Adam's adjusted total value all the way down here, and now much more in line with all the others. In fact, you can see that the average order value, I guess it's a bit hard to tell, but it's somewhere just below 10 and maybe above 5. So you can see that the blue users, like the users down here, they were all adjusted upwards a little bit. And the users up here, they were all adjusted downward a little bit. And Adam is basically just the extreme example of this downward adjustment. If you then were to estimate the same sort of distribution of the t-statistic under the null with this adjustment, then you end up with this purple line, solid line here that now looks much, much closer to the standard normal. You can still see that there's some small sample issues going on. There's still a bit more mass on the lower end, and it's not, there's some mass missing here, but on average, in general, the mass outside of the critical values is now much, much closer to 5%. And we got rid of that second hump here, exactly because Adam now isn't such a strange outlier anymore with his or her ordering behavior. So by using this this Rasch adjustment, you can both have reliable inference in terms of your variance estimator, even when you have very large or skewed clusters in your experiment. And you, in theory, at least, come up with an unbiased estimator of your treatment effect, something that isn't true for the other two I discussed earlier. Now, what is true is that here too, the bias shrinks with the number of users or the number of observations in your number of randomization units in your experiment. And depending on the size of your experiment, the bias is probably not really a huge concern. It becomes more one of getting the variance estimator right. You can, this estimator too, apply in a regression setup where you simply regress the transformed outcome X on an indicator W, using again HC0 standard errors to basically get the correct variance estimator. And then the only reason why I've called it X here instead of anything else is because the adjustment for the regression looks slightly different than the one I discussed earlier for deriving it as a difference in means by hand. So if you do want to use it with a regression, please be careful that the adjustments looks a little different. Okay, so what have I tried to tell you or hopefully introduce you to a little bit over the last 40-ish minutes? There were three things I wanted to sort of walk you through. The first one is the statistical model that's often used for experiments, and in particular highlighting the difference between the sources of uncertainty for experiments. In experiments, we most often think about assignment uncertainty as the relevant level of uncertainty, and that contrasts with the concept of sampling uncertainty, which is discussed in many textbooks that don't explicitly deal with experiments. And it's particularly true for those of you that read econometrics textbooks. They almost all deal with sampling uncertainty. The distinction matters because the properties of the estimators you use for your experiments and try to base your decision-making on are affected by the model you choose. If you think about a world of assignment uncertainty, then you need to also think about the properties of your estimators through that lens and not simply translate whatever you've learned about sampling uncertainty. Most of the time, that there are ways of guarding against that. So if the randomization unit is identical to the analysis unit, then the model with assignment uncertainty tells us that using covariates can lead to biased estimates of the average treatment effect. They're not unbiased anymore. The bias is easy to check because you can simply compare it to the difference in means estimator. And then if those two outcomes are fairly close to each other, from a business point of view, not meaningfully different, then you know that bias isn't a problem in your specific application. If you do use covariates, always, I suggest always interacting the covariance with the treatment indicator and not just putting the covariates in there by themselves or only by themselves, because you may actually end up with worse inference. And that's a little harder to detect, actually. So there's really no reason to not interact them. If, however, your randomization unit is coarser than the analysis unit, then even the simple difference in means estimator may be biased, and you will probably have faced challenges with your inference even when you think bias isn't a problem. In that instance, consider using this Rasch estimator that I introduced and linked the paper that actually does the derivation. It's not super difficult to do, especially if you have a good source of pre-experiment data that allows you to estimate this adjustment factor K. And as David said initially, I'd be more than happy to discuss questions now or later in the chat. We're also hiring, so if you are interested, if you find causal inference interesting, drop me a line and we can have a chat separately about that too.
Perfect. Thank you very much, Matthias. That was absolutely fantastic presentation. And yeah, really good numbers of people watching along at home. So yeah, I think it's gone down very, very well, actually. So if it's okay, we'll keep things moving along. First of all, in terms of professionalism, you finished bang on Q2. That is some next level stuff, Matthias. You can come back. We'll have you back.
Thank you. I'm glad I passed that test.
Perfect. We'll jump into some questions. If it's easier, actually, you can open the Q&A feature on the side and you're able to read along just as I'm reading them out as well. We'll go to the first question from Benjamin there. He says, hi, Matthias. Thanks for the excellent presentation. My first question is, when have you found these adjustments useful in practice? Is it when there is a larger gap between the unit of randomization and the unit of observation?
Yeah, so that's a really good question. In the presentation, I discussed the difference of a user level experiment, a user randomized experiment and analyzing an order level metric. That is not actually a great example for where we found these methods to be most useful. Most of the time, we have found them to be much more valuable when we need to analyze at even coarser levels than that. So for example, a zone level or cluster level or even a city level, because it's some specific marketing experiment where you can't control who sees it or who doesn't. It's like, say, it's some above the line marketing. And then when you randomize at the city level, you automatically have a lot fewer cities, so a lot fewer randomization units. And doing order level metrics then, so I think that's what Ben means with the gap there, unless I'm wrong, misunderstanding it. At that point, that method is really valuable, much more valuable than in other cases where you really randomize at the user level.
Perfect. Thank you very much. We're going to jump up to that question there from Zhao Hong Wei. Should the variance calculation be non-independent based, i.e. it should not be a simple sum of two, because if the size selected to be treatment group is high, means the size selected to be control will be less, given a fixed total sample size that you have?
So if my apologies if I misunderstand something here. The way I interpret this is that that question refers to this very simple standard formula of the difference in means estimator that I had put up on one of the very early slides.
Yeah.
And there it's the sum of, or what I put up was the sum of the variance of the mean in treatment and the variance in control. I believe that that's correct, and it isn't, and these two really are independent because of the randomization we've used. It's randomized across users so that the users in control and the users in treatment are completely independent of each other. And thus the variance is truly, the variance of the two means is the sum of the variance of the means. As I said, my apologies if I misunderstood the question, but I think that's how I would answer it.
Thank you very much. I think that'll probably lead into the question from Raphael there, actually, because I think there's probably a few people that would like to look back over this, perhaps in more detail, slower pace and stuff like that. And Raphael was asking, thank you for the great talk. Have you got a paper, blog post that corresponds to this that we could perhaps refer back to in the future? The session has been recorded, which may be one option, but I don't know if there's anything else that you can recommend to Raphael.
Yeah, so what I could offer, if you weren't, and presumably you weren't, my apologies for that, fast enough to note down the footnotes I had put into the slides, I could offer to post them in the DSF events Slack channel for people if they're interested in that. Obviously, as you said, David, people can watch the recording, but I can also offer to post the references there.
Perfect. Thank you very much. And then we've got one more question from Benjamin. He's basically saying, in relation to the parameter K, have you found this parameter to be relatively stable in practice? Are there any issues for external validity when comparing across experiments?
Yeah, so we have not at least I'm not aware of us having looked into how stable this parameter actually is. The way we usually convince ourselves that it's stable enough is by running some pre-test on the experiment to make sure that it actually gets us the inference to where it needs to be, meaning close to normal 0, 1. So I sort of have an indirect answer to that first question. The second one, issues for external validity when comparing them across experiments. I haven't actually thought about that. I would have to spend some time thinking about that. So I don't have a good answer to that, actually.
Okay, thank you very much, Matthias. I think I'd just like to wrap up by once again reiterating my thanks to Deliveroo. I think the thing that I love about them as a partner is that they're always at the forefront in terms of the type of challenges that they're working on, and they're very proactive at sharing with the community as well. So Matthias, your talk today I don't think was any different to that, and it's really getting under the hood and giving people some real world examples, which is really much appreciated. So thank you very much to you, Matthias, for giving up your time and coming presenting for the community. I hope you've enjoyed it, and we'll if possible, we'll have you back in a real world environment at some point in the future.
Thank you very much, David. It was a great fun. Thanks a lot.
Perfect. Speak to you soon, Matthias. Thank you all for joining us, and we'll be back with you throughout the rest of November. Have a good one, everybody.